Hello, everyone. Uh, I hope you had a great day so far. Today, we are gonna focus on some example to kind of uh, close the chapter 3, which is the time domain analysis, and go over those concepts that we discussed. And next week, we are gonna talk about the time response, which is our next chapter. So, is there any question generally regarding what we talked? No? Okay, so let's start our discussion about the example that we now, the first example, the first example is a first order low pass RC circuit that we want to analyze and find the transfer function out of the differential equation. Okay, now the transfer function that we want to find is going to be the output voltage, which is the voltage across our capacitor over the input voltage that we have in our circuit. Now, since this is a first order circuit, that means the equation that we are going to have is also going to be first order. So basically, the state space model is going to be the same as the equation itself. Okay, so to run the analysis, we are going to have we have to do a KVL in our circuit. If we do the KVL, we are going to have our input voltage equal to the voltage across the resistor, which is the resistor times the current plus the voltage across the capacitor, which is the C, sorry, the 1 over C, okay, over times the integral of the current. Okay, now this is our VI. Another way to describe that is since we can differentiate this equation to get rid of this integral, okay? And we already said that when we wanted to have a transfer function, the input is going to be the step function, okay? The differential of the step function, the differential of u of t, I believe you remember from the calculus, the differential of the u of t is the initial condition times the delta drop, okay? Which, again, based on the assumption that we have when we want to follow the system, our initial condition is 0, so basically the differential of the input is going to be 0. So what we are going to have is 0 equal to the R I square, the differential of the I plus 1 over C times I. Now, that says in that equation, you can easily find that the R di over dt is going to be equal to the minus 1 over C times current. Very good. But what is the current? Since this is a simple one loop circuit and they are in series, that means they share the current. So you can find the current from two ways. One is we can find the current from the resistor, which means the voltage across the resistor. Current goes that way, which is V input minus V output over the resistor, or we can find the current based on the capacitor, which is the C times the differential of V out over dt. Okay, now if you implement the I into your circuit, you are gonna see that the equation based on V out is gonna be basically the equation is gonna be VI is gonna be equal to the V out RC V out dot, which is the differential of the V out plus V out. Okay, now this is our VI. Or if you take a Laplace transform from this equation, you are going to see that Laplace transform of the input voltage is going to be the Laplace of that input voltage. We are going to keep it because we need it. The RCV dot is going to be the RCS. We have a +1, and the output voltage is going to be simply the Laplace of the output voltage. So if we want the V out over VI, and we have the formula that relates the V out and VI, therefore we can easily find the HS, which is our transfer function, which will become 1 over 1 plus RCS. Is that clear?
Can you please? VI
This one?
the previous.
This one? This is the KVL that we have. This is the KVL that we have. We just replace the current into that KVL. Okay, and if you drive that, you're going to see this one. Another way to do that, let me give you another way, is that we have the currents. We have the currents. Okay, this is maybe the simpler way. Okay, we have the current and we know they are equal to each other. Okay, so another way to do that is to just simply create the formula of IC equal to IR. The IC is C dV out over dt equal to V input minus V output over R. That means we have V input equal to V output plus RC, the differential of V output over dt, which if you run again a Laplace transform, you are going to see the same equation that we find out. Is that clear? Are we good on that analysis? You want to write it down, or should I? Or is that because I wanted to like? Okay, yeah. Are you okay? By the way, I don't know if you noticed or not, I am recording the session and I'm posting on Canvas. So if you want to review anything, you have the access to the videos. Okay, so if you kind of like missed anything, don't worry about that. You have the access in the to the video record of the session on Canvas. Okay. Okay. Let's run another example. on a first order system, and we wanted to like analyze it. Another example is an RL series. We have a resistor, we have an inductor, RL, and we have our input. And what we wanted to like have is the h of s, the transfer function, as the output, which we assume is the current of the inductor, so the IL over our input voltage. Again, to run the analysis, I of the inductor, IL. Now, to run analysis, again, we do the KVL. We have a loop. We do a KVL. If we run a KVL in our loop, we are going to have the input voltage equal to the RI plus the L di or dt. Okay, so if we have that, we simply can get a Laplace from it. So Vs is going to be the Ri, and this is one loop. So the current and the inductor share the current. So this is going to be, both of them are going to be IL. So this is going to be IL plus LS IL. Now we want IL over input voltage. So it's very simple. The h of s is going to be 1 over LS plus R. Same as before, you run a KVL over your circuit, you have a differential equation, you take a Laplace transform, and then you basically develop your transfer function based on the output and input that you have in your system.
But where is the 1 over LS plus R?
It's came from here. You have Ri of L plus LS I. So this become actually R plus LS times IL. We want IL versus Vn. So this means is going to be 1 over LS plus R. So this coefficient goes here. This Vin goes in the bottom denominator of that IL. And then you have a transfer function. Any question? No? Okay, let's move on to another example, which is a second order circuit. In our second order circuit, we are going to talk about a series RLC. Okay. And what we want as h of s is the voltage across the capacitor over the input voltage. Now, we have several ways to deal with that. Okay. In frequency domain, we learned that we can simply replace the components with their impedance. Okay. And if we do that, basically, we have our S-domain circuit. Okay, so this one become 1 over CF. This one become LS. Okay, and you simply can run a KVL. So VI is going to be RI 1 over CS. Let me do that. One way is to simply shift this to the S domain, which become the V of S, V in of S. The impedance of the R is the same as R. The impedance of the C is going to be 1 over CS, and the impedance of L is going to be LS. So if you run a KVL, you are going to see that V of in S domain is going to be equal to the RI plus 1 over CSI plus LSI. Okay, and V of C, which is our output, is going to be 1 over CSI. So V of C over Vn is simply dividing this part, this equation, by this equation. So H of S become 1 over CS times I, and this one is R plus 1 over CS plus LS times I, and the I cancel each other on and out, and you have your transfer function. Okay, this is one way to deal with that, but we wanted to have a hard time and go through the differential equation of that circuit. So we are going to run an KVL over the original circuit. If we run a KVL over our original circuit, we are going to have the input voltage equal to the RI plus 1 over C, the integral of the I, plus L di over dt. We don't like integral, so we are going to take a differential. This is one way to do that. Okay. Now, before I take a differential, in the previous example, we simply get a Laplace transform of this KVL and we find out our transfer function. You can do that. Okay, it's maybe easier. You want to do that? Let's do that, and then we have third kind of option. If you run a Laplace transform, it is gonna be V of S R times I of S plus 1 over CS times I of S plus LS I of S, and again we know that the VC is 1 over CS I, so like before we can find the H of S. Okay, this is the second way. Now the third way is to fully go with the differential equation, because we know how to have the state space domain, correct? So we are gonna take another differential from this KVL. If we do that, we said this is a step function, so this is gonna be V0. Okay, the differential of this one is gonna be di over dt. This one become 1 over ci, and this one become L, the second order differential of I. Are we good? Now, are you good with the red part? I wanted to erase that. Okay. Now we have a second order differential that we don't normally like, so we wanted to use the state space model. And we know if we have a second order differential, that means if we wanted to do the state space model, we need two state values. Are we good? So we are going to have x1 and x2. We name x1 as our variable inside the circuit, so it's going to be current. And x2 is the differential of that, so it's going to be di over dt. So now we having our system, the state variable. We want to develop x dot over equal to ax plus bu. So we need the x dot vector. x1 dot and x2 dot. x1 dot is di over dt, which is x2. And x2 dot is going to be the second order differential of our current. Which we can find it using the original circuit. And we know if you do that, the second order differential of the current is going to be, this is minus R over L, this is L, di over dt. I bring this, the first and second term, to the other side of the equation. Minus 1 over LC I. Very good. Now, let's do that. If we do that, we have x2 dot as this is x2, this is x1, right? The first differential is defined as x2, the I itself is defined as x1. Are we good? Now, so this one become minus R over L times x2 plus 1 over LC times x1. Now we have our basically the state variables and the differential of the state variables. Now we can develop our state space model. x1 dot, x2 dot is equal to that A matrix times x1, x2 plus, this is going to be 1 by 1 matrix. Okay. And we are going to see what's going to happen. Now, here, as you can see, we don't have any input. So this is going to be 0. So we basically can ignore this one. X dot 1 is equal to the x2. So this is 0, 1. Very good. Now, x2 dot is equal to the minus RL x2 and 1 over LCX.
So minus 1.
Yes, sorry. Thank you. Now you have your state space model. Okay, how you can develop the transfer function out of this state space model, we already know. The y of S. Now let's actually define the output. The output is the V across the capacitor. Okay, so our output is V of C, which is 1 over C, the integral of the I dt, I dt. Now keep that in mind. We are gonna use that. Here our differential, here our state space function is simply getting the Laplace of this. So this one become S times x1 dot x2 dot equal to, these are zeros, 1 over LC RL. X1 is I itself, so we are going to keep it as x1. X2 is the differential of the I, so we are going to name it as SX1. Now, when you have that, the transfer function is going to be the output C Si minus A inverse times B plus D. D is 0, so we don't care about that. Sorry, B is 0. B is 0. You have that. So Y is basically gonna be whatever matrix that we have for D in this specific case. Are we good?
As x1 on the
Yes. I just replaced this with the definition. X2 is the differential of x1, so it's SS.
right.
Okay. Now, it's kind of like doesn't work for us because our B is 0, and basically the first term, whatever it is, becomes 0. Okay, so we only have the D. Now look at this one. This is Y equal to VC 1 over C, which is 1 over C integral of the integral of the current. Now, what is the current here? Because we want to have the HS over V in, so we wanted to like replace the current. Okay, we can use the KVL to find what is the 1 over integral of the 1 over C integral of the current, which is gonna be equal, or Y is gonna be equal to the V in minus Ri plus minus L di dt. Are we good? So you can take a Laplace out of this, and you can develop the transfer function, that D matrix. This is LS, okay? This is going to be Ri, this is going to be Vn in the S domain, and you have your basically Y for your transfer function. Which again, you are going to find out that the transfer function is what we found over, what was that? Oh, I erased it. 1 over CS over LS squared plus RC plus 1. Okay, now, what would happen if we wanted to like just calculate this part? Now, if we wanted to like use this part, we know the VI is R plus 1 over CS plus LS times I, and our output is 1 over CS times I. So the H of S is gonna be VC over VI, 1 over CS over R plus CS plus LS. If you do the diligent for bringing this CS down, you're gonna find out that the H of S eventually become 1 over LC squared plus RCS plus 1. Getting a differential from the getting the Laplace transform from the differential equation is easier than the steady space, but we already know how to go over the steady space and find out our transfer function out of the steady state. Now, what if I wanted you to find out what is the impulse response of this transfer function? How we can find the impulse response, impulse, not the step function response, impulse response of a transfer function. Impulse is delta d1.
So just the first Laplace
Now,
or like P and P.
it's taking more than that. Okay, let's do that. I have to erase this state space. Our h of s that we found is 1 over LC s squared plus RCS plus 1. Okay, and we wanted to find the impulse response. Impulse response. Impulse response, this is y. This is this HS is output versus input. Right? So our output, let's say our output was VC over our input. If our input is impulse, which means the V in over time in time domain is the delta Dirac function. From the table that we have, if you remember, the value of the Laplace transform of the delta Dirac is simply 1. Okay, so if this is 1, that means output is equal to transfer function itself plus RCS plus 1. Now, how we can transfer that into a time domain function? We want to find VC in a time domain. This goes with like a little bit of like mathematic tricks. Okay, now we have a second order equation at our denominator. Correct? We have to simplify it in a way, or like change it actually in a way that we can use that table that we have for Laplace inverse. One of the famous kind of like a function that we know how to get the Laplace inverse and Laplace transform. Okay, how we can do that? Now, this is a second order equation in S domain, which means a second order differential equation. Remember that? What is the response, the impulse response? I believe you already should talk about that in calculus and in circuits. At least I hope so. What is the impulse response? What type of function would define the impulse response of a second order system? What do you expect to have as a function out of a second order system? What do you call a second order system in general? The second order system is a oscillator, is oscillation system.
It's like a damped cosine or sine wave or something.
A damped kind of sinusoidal equation. So knowing that, That means what we need to do is to turn it in a way that either this transfer function become the Laplace of a sine function or a cosine function or both. Does that make sense? Now, how we do that is a little bit of mathematics here. Let's simplify and the notation here, the indexes here, and make it a standard second order equation. The standard second order equation means that the second order term coefficient should be 1. This is a standard way. Okay, so if you have, like, let's say this, let's call this one omega n square and this one 2 alpha. I'm naming that because I wanted to like use the standard equation. If you remember the standard differential equation, the standard differential equation is x double dot plus 2 alpha x dot plus omega n square x equal to 0. This is the standard differential equation, which that alpha you might see that as cosine omega. Okay, that's another notation to show the alpha is actually the formula of the alpha. Okay, now if that's the case, that's why I named these two alpha and omega n, because I want to follow the standard representation of a second order equation. Now, let's play with this equation, okay, and see what's going to be, what type of function we are going to end up. First, we are going to make this one a standard equation, so it's s squared plus r over L s plus 1 over LC. I just made it a standard. Now, I named this one 2 alpha and this one omega n squared. Here, omega n squared. So I can play with this function and add, see, this is S2 plus 2 alpha S plus omega n squared. Look at this term. Does it remind you of a certain function? A certain famous second order equation? What is that? When you look at this s squared plus 2 alpha s, what is the first thing? What is the first second order kind of like term comes into your mind? Anyone? Okay, let's remind it. One of the famous one that you see in the calculus or like in algebra is that s plus alpha squared is going to be s squared plus 2 alpha s plus alpha squared. Remember that? So, if I can make these two terms somehow into the famous second order equation, okay, I can simplify and have a second order function of s, okay, which you know we have both in the denominator of the sine and cosine. You remember that? So I am gonna do plus minus alpha squared for the denominator. What that means? That means my transfer function or my output basically right now is going to be 1 over, the output is going to be 1 over s plus alpha a square plus omega n square minus alpha square. Are we good? Now I have a very close Laplace that is to the Laplace of the sine equation, the sine function, right? What is missing? If I wanted to what is missing? What is the difference of this Laplace function that I have with the Laplace of the sine? It is still not the Laplace of the sine. What should I do to that to make it the Laplace of the sine function? What is missing here? What was the on the denominator? On the denominator, you have to have the square root of whatever you have here that is plus by the s term. Correct? So I'm gonna multiply and divide by that square root. So what's gonna happen is that my b of c is gonna be equal to that the square root of the whatever we have here, omega n square minus alpha square. Okay. And I have omega n square minus alpha square s plus alpha square plus omega n square plus alpha square. Are we good? Let's name this part omega d for simplification. So this is going to be omega d square. This is going to be omega d. And also this is going to be omega t. Are we good? Now we have Vc equal over the 1 over omega d over s plus alpha plus omega d squared. Now, take a Laplace inverse from this function and tell me what is going to be our Vc of t. Any suggestion? This is 1 over omega d. This is a constant now. What was the linearity characteristic of the Laplace? Any constant number times the function would be that number times the Laplace of that. So this one would not change anything. It's just a coefficient. So we have 1 over omega d here.
Is it sine?
Sine of
Sine. Wait. No.
sine of omega d times t is a t function, right? So we have sine of omega d times t. Are we done?
No. Alpha's in the
We have a s shift, right? What would e to the power of that minus that shift? So we have e to the power of minus of what? Are we good? Now you remember what was the response, the impulse response of the second order system? It is a decayed sinusoidal. Right? That famous response. Are we good? Any question about that? So this is how you can get a transfer function. If you know the input, you can get out. if you have RLC in parallel, okay, it's gonna be the same kind of analysis. The only difference is that you run a KVL here, but if you have an RLC parallel circuit, you just need to run a KCL at the node. So over there we run a KVL if we have a parallel connection. The only difference is instead of a KVL, we run a KCL here. And it's going to be the same process. Are we good? Okay, now let's see what would we have what would we have. Let me do the next, because I don't know if I make it. But this one is more important. Let's say that we have a transfer function g of s as the second kind of like a transfer function, second order in the denominator, like beta 2 s squared plus beta 1 s plus beta 0. Then we have s cubed plus alpha 2s squared plus alpha 1s plus alpha z. This is a general form of transfer function with the second order in the denominator and third order in the denominator. Now, please note that in a denominator, I have a standard form. So it's better for you, and it's actually a very kind of like popular kind of like method that whatever equation that you have in the denominator, make it a standard. So the first term, the highest order coefficient is 1. Okay, now how we can get a state space model from this? You remember the thing that we taught about getting a state space out of a Laplace transform? Anyone can tell me what was the first step? What is GS? What is the definition of GS?
Yeah.
What was the definition of a transfer function? Output versus input when the initial condition is 0. Correct?
Yeah.
So this is output versus, let's say, input, and is equal to this function. Okay? Beta 2 is squared plus beta 1 s plus beta naught s squared, alpha 2 is s cubed is square alpha 1 s alpha. Now I want a transfer function to change it to the state space. So I need a differential equation. And the transfer function that we had, the state space model that we had should represent the differential that relates output versus input. So what we had is to simply make these transfer function into a function of ys that is equal to another function of rs. So what we had was the denominator sq times ys was equal to whatever we had in a denominator times input. Next step, what was the next step? To get a Laplace inverse. Remember? So x cubed ys, the Laplace inverse of that is third order differential of ys. So it's gonna be y triple dot. Very good. This one is gonna be alpha 2 y double dot, alpha 1 y dot, alpha 0 y. Same here. Beta 2 r double dot, beta 1 r dot plus beta 0 r. Okay, I used the lowercase, so let's see if be consistent. Very good. We have a second order. We have a second order equation. How many state variable we need? Sorry, the third order equation. How many state variable we need? 3. So our state variables are gonna be x1, x2, and x3. We said x1 is always the function itself. x2 is the differential, and x3 is y double dot. Now, before I move forward, what is missing here? I missed one step. What is missing here? Anyone knows what should I done to this transfer function before I move to the rest of it? What we want is x dot equal to ax plus bu, which is r. Let's say b. And y is cx plus d here. What I missed? We already had such an example. I missed a step, which is an important step. Do you remember that block diagram that we talked about? Yeah. So if we want to have both x dot and y, we need to first change this one to 2 transfer function. Remember that was the step that I missed here. So let's correct that. I am gonna define the ys over rs as cs over rs. I am defining a new component, a new ancillary kind of like value, times ys over cs. That series block. And I know this one is that 1 over s cubed alpha 2 s squared alpha 1 s alpha 0. And this one is the denominator. this part would give me the x dot, and this part would give me the function for y. Remember that? Now, let's run the correct answer. CS over RS is this transfer function. Easily you can see that the CS times the denominator S cubed alpha 2 s square alpha 1 s alpha 0 is equal to the RS. Very good. Now let's then do the time domain. C triple dot plus alpha 2 C double dot plus alpha 1 C dot plus alpha 0 C is equal to the we have a third order. We need 3 state variables. The first one is the function itself, C. Second one is C dot. Third one is C double dot. That means my x dot vector is going to be x dot, x2 dot, x3 dot, x1 dot is C dot, which is x2. X2 dot is C2 dot is x3. And from the original circuit, we know that the x3 dot is going to be R minus alpha 2 x3 minus alpha 1 x2 minus alpha 0 x1. Are we good? Now, what would be the function? A x dot equal to the ax plus bu, or x dot is going to be x1 x2 dot x3 dot equal to the third order matrix that we have, 3 by 3 matrix that we have, times x1 x2 x3 plus 3 by 1 matrix times u, which our u is r. Are we good? x1 that is x2, so 0 1 0. This is going to be 0 0 1, and x3 dot is going to be minus alpha 0 minus alpha 1 minus alpha 2, and here we don't have an r. We don't have an r. This one is 1. So we have our first equation. Now, what about the second equation? That y equal to the cx plus du. Now, we know that this is the function that describes that we use for this one. So, from this function, we know that y of s is c of s times beta 2 square s square beta 1 s beta 0. Time domain of that is going to be y of t, or let's ignore the t. This is beta 2 c double dot beta 1 c dot beta 0 c. But we already know from our state variable that this is going to be beta 2, where is that? x3 plus beta 1 x2 plus beta 0 x1, and we don't have any r in it. So what would be our equation? We only have one y. We have the C matrix, which is 1 by 3 matrix times x1, x2, x3 plus that D matrix, which we don't have anything to 0, but I'm going to write it R, but we know this is 0. Okay, and our A matrix, as you can see, is the B0, B1, and beta 2. Now, I want you to look at these two equations, the one that we have for x dot, the one that we have for y, and look at the transfer function general equation. You can already see, okay, you can already see that if you have a transfer function, then the denominator is one order less than a denominator. Is that clear? One order less than a denominator, which basically what we call it is a kind of like a controllable canonical form of, system. You can easily develop, I'm gonna erase this, develop and find out the A matrix, B matrix, and the C matrix. Okay. Using the GS alone, the A matrix, the first two rows, based on our assumption and definition, is always going to be 0, 1, 0, 0, 0, 1. That's given. The third row is going to be the minus all those coefficients in reverse order. So first time alpha naught, then alpha 1, then alpha 2. So minus alpha 0, minus alpha 1, minus alpha 2. Make sense? Remember, this should be a standard form. The denominator should be a standard form. So by looking at this function, you have the A. Correct? Now, for the B, again, because our definition of the state variable, okay, because of the definition of the state variable, we know already that x1 and x2, okay, all the x's beside the last one do not gonna be affected by the input. So whatever we have here is 0. Only the last state variable has the input in it. Okay. So what's gonna be that input? If you cannot factorize any coefficient, that input would be 1. But if for some reason, like for example, you can factor out all of them are even number and you can factor out like 2, then this the denominator of this function, instead of 1 over denominator, is going to be 2 over denominator. Do you see what I'm saying? So then that 1 becomes 2. Does that make sense? Is that clear? Now, what about the C and the D function? In such a system, the C function is always the coefficients of denominator, but in a reverse order. So it's going to be beta 0, beta 1, beta 2. Remember, in A, we have minus those coefficients. In C, we have the coefficient itself. And in such a function, D always is 0. So if you have such a transfer function, only by looking at it, okay, you can find out what is the A, B, C, D, and like find out the steady space model in less than a minute. And to be honest, normally this is a very kind of like normal system transfer function. It's happened a lot when you define the system and you want to like design the system or analyze the system. So it's good to know how to find this. You are gonna see this type of function quite a lot, especially when you have higher order. That will help you a lot. Like if it's fifth order and this one is 5 order, okay, running a matrix like 5 by 5 or 4 by 4 is not going to be, that easy. Is not complex, but it's time consuming. So you can easily find those values. Any question? Are we good? Now, in the file that I uploaded here, I don't have a time to do that, but in the file, I already put another example, which is for the system, like a transformer that has a mutual kind of like factor, or what we mean is that the x1 and x2, okay, are not fully kind of like independent of each other. They are not linearly independent. They're non-linearly independent. So the system has like kind of a memory, like a transformer. When you have first side, the primary side inductor, the secondary side inductor, and you also has a mutual inductor between the first, the primary and secondary. I believe you already aware of that. Are you? Did you cover mutual inductance in any of your courses? When the transformer, primary and secondary, are not just an independent inductor, they also have a mutual inductor because they affect each other. In reality, you consider the primary and in ideal form, you consider the primary and secondary isolated from each other, but that's not going to happen in reality. The magnetic field created by the first one also would have effect on the second one and vice versa. So we have a mutual inductor between the two. Search on that. I think you should have that in either like one of the power courses or the circuit one. Okay. But if not, search on that. Okay. And I already have the equations in the examples that I have. So I think is the one before the last example when we have a coupled RL circuit. So those inductors are coupled to each other like transformer. Okay. So we have a mutual kind of like a parameter that relates the currents of the first inductor and the second inductor. Okay, so it's not just the first order equation anymore, simple equation anymore. It is first order equation still, but it's not like a standard that you need, that you could see. Does that make sense? Look at the example. If you have any question, let me know. If you have such a system, then your transfer function would not be a simple function. This becomes matrix itself. Okay, so the transfer function becomes matrix. You can see that I already put that in the example, but if you have any question, I'm not going to put that in the exam or something, but it doesn't matter. You need to learn. Okay, so if you have any question, let me know. Okay, but the coupled system are very important. You are going to see that a lot in a practical kind of like analysis that you have. Okay, so go over that. Any question? No? Are we good? Okay, so thank you very much. I will see you next week.